Hi, everyone. Welcome to this lecture for this random section in Chapter 8, Chapter 8.1. Chronologically, if you're watching these in the order in which they're intended, we're doing Chapter 8.1 after doing Chapter 2. So you're kind of like, how do we jump all the way there? We eventually jump back to Chapter 3, but 8.1 is a section that you really could do a lot earlier. You could do it as early as after Section 1.1. However, since some of the meaning of the section is rooted in graphs, you should more likely do it after 2.3, but instead of breaking up a chapter in the middle of it, I think it's better to just throw it in at the end. So after chapter 8.1, just this one section, we'll jump back to chapter 3 and talk more about specific types of functions and the fundamental theorem of algebra. But until then, this section is actually pretty nice. This is a pretty popular section. A lot of the things you can do here are very nice to do in a world where we enjoy things that are kind of ASMR and cleaning videos and all that. This is a section that it's nice to eliminate some things. So here we go without further ado. So not multiple sections, just multiple things. We're only going to do these first two parts. This last section, I just got really bored one night and decided to do all the same problems, but swap the method in which we do them. So we're not going to go over that. But if you want to see it, by all means, I can give you this presentation. All right, so some basics. We started solving equations in one variable with answers like x equals, right? 1.1, 1.3, we had answers x equals this. Then toward the end of chapter 1, we solved inequalities that had solution sets like x is greater than some number or x is less than or equal to some number. Then we looked at graphs, which were technically collections of solutions, right? We said 2, 5 fell on one specific graph because it was a solution to the equation y equals whatever it was. And then what we're going to do now is solve systems of equations where the solution is also a single point x comma y. So graphs are collections of solutions. But what we're going to do now is look for a single point that satisfies two separate equations. So our focus in this section is two linear equations and two variables. However, you can get really, really funky with this type of stuff. You could do three linear equations and two variables. You could do 3 and 3. You could do 2 and 3. You don't necessarily have to do linear equations, but for the purpose of what we're talking about in algebra, the scope of this course, it's fine for us to do two linear equations in two variables. So how we verify a solution is similar to how we verified solutions in the past, except now we're going to plug in x and y to whatever our system is. So systems will look like this. Not always necessarily with a bracket, but I like putting the bracket there to show this is the system. So now we want to know, is 3, 1 a solution to this system? Well, we can tell if it's a solution by plugging in 3 for x and 1 for y, but not just into one of these equations. We want to plug it into both equations. So let's substitute 3 and 1 for x and y respectively into both equations. 2 times 3 is 6. 2 times 1 is 2. 6 minus 1 is 5. 3 plus 2 is 5. Well, normally we're only satisfying one equation. So if it satisfies one equation, then we're good. But here in systems of equations, we are just trying to satisfy every equation. So for example, if this was 5 equals 5 and 5 equals 4, 3, 1 would not have been a solution because it doesn't satisfy both equations in the system. 4, 3, for example, if we plugged in 4, 3, well, in the top, we get 5 equals 5, but in the bottom, we get 10 equals 5. So for example, this would not be a solution because it doesn't satisfy both equations in the system. So one way you can solve is actually via graphing. Notice that I said that these are linear equations. Well, if they're linear equations, that means they are just lines. So the solution to a system would be where those two lines meet. So if we were to graph 2x minus y equals 4 and 2x plus 3y equals 12, well, let's get them both down to y equals something. And when we graph those two lines, this is what we get. And then the point at which they meet is the solution. Well, that point is 3 comma 2. So if you were to go back and plug in 3 comma 2 to each of these equations, your system would be satisfied. Okay, so we have some types of solutions we can also get. Most solutions are going to be x comma y's, but you could get to a point where a single statement in your system is never true. In that case, the system is what we call inconsistent. Oh, that sounds familiar to how we've solved equations and inequalities in the past. This is similar to no solution, and when graphed, these lines are parallel. So if you get an inconsistent system, it means that the lines are parallel and they never meet. Well, if they never meet, you can't have a solution. So there's that. If you get to a point where you have a statement that is always true, right? For example, 5 equals 5, then your system is dependent. Well, this is similar to all real solutions. It means that every solution on the line is a solution. And when graphed, these lines are actually the same thing. They overlap everywhere. Now, there's actually some deeper meaning here to dependent solutions. And there's such a way you're supposed to write dependent solutions. However, for the scope of the specific course that I have taught, we don't go into that. But if you ever take a class like linear algebra, or you spend a little bit more time in this type of chapter or this section, you will do some weird things with dependent solutions. But again, not the scope of our course, but it is something that is of note. Okay, so most importantly, we want to talk about the methods. So there are two algebraic methods. One method is to graph, right? We just did that. But there are two methods that require no graphing at all, and they are substitution and elimination. Substitution says we are going to solve one of our two equations in the system for x or y. Well, so now we have x equals or y equals. Once we have x equals or y equals, we're going to take that and plug it into the other equation, right? There's two equations in our system. So what we're going to do is take one equation, plug it into the other. Well, once you do that, what you end up getting is a single equation in just one variable. You might have all x's now or all y's now. In that case, you solve that equation for x or y, and then you would take that x or y that you get a value for and plug it into either original equation of the system. Well, that's substitution. My personal favorite, however, is elimination. And elimination, what we're doing is eliminating one of the variables. So what we want to do is add or subtract the equations to eliminate that variable. So one thing that you should note is that you might need to manipulate your equations to be able to do this. For example, if you add or subtract the equations right away, it's totally possible that you will get x's and y's in your added or subtracted equation. So what you might want to do instead is manipulate the equations, multiply by some type of constant, so that when you go to eliminate, one of the variables actually eliminates. Well, once you eliminate x or y, now you can solve for the other variable that you did not eliminate. And now it's back to the original question, or and now it goes back to the last method that you have solved an equation for one of the variables, and now you just plug that variable into either original equation. So let's just do these algebraic methods, handful of examples. So this first one, I want to solve via substitution. X minus y equals 5, 2x plus y equals 7. You could do this with elimination, but again, I'm showing it with substitution just so we see the different things. If your method works and you like sticking to one method, if you get the right answer, you get the right answer. So here's what we're going to do. We're going to solve the first equation for x. Again, not the only option. You have two options for method you use, and then after you choose your method, you have two options for what variable you either solve for or eliminate. So not necessarily any one correct way, but so it goes. All right, so let's solve the first equation for x by adding y to both sides. Okay, and what we're going to do now is we have x equals y plus 5. So what we're going to do is plug in y plus 5 for x. We got x equals y plus 5. So plug in y plus 5 for x into the second equation specifically. Oh, well, why don't you look at this equation down here now? This equation is just a simple linear equation that we have solved all the way back in 1.1. So let's distribute 2. Let's combine 2y and y. $2 plus $1 is $3. Let's subtract 10 on both sides, and let's divide both sides by 3. Okay, so we have the value to one of our two variables. We have that y equals -1. Okay, well, if we know that y is -1, plug -1 into the first equation. Well, y is -1, -1 plus 5 is 4. So the solution to the system is 4, -1. However, you could have plugged y equals -1 into the either original equation in the very beginning. So, the way we're writing this here is that, the second equation kind of goes away, just becomes this y equals -1. But you could plug y equals -1 into the original second equation, and you would get the exact same answer. So not perfectly a rhyme or reason any one way or the other, just something to keep in mind. Okay, and like I said, is this the only way to do the problem? Did we have to substitute y plus 5 in for x? Did we have to use substitution at all? Stuff like that. Again, I bring up that multiple paths can get you to the same answer. Okay, and if you were to graph those two lines, there you go, 4, -1. All right, let's solve this one via elimination. 3x plus 2y equals 3. 9x minus 4y equals 4. So if you're looking for an idea as to whether or not you want to use substitution or elimination, this example is great to not want to do substitution. If you were to do substitution, notice that you would need to solve for x, and at some point, you would need to divide by 3. So you would subtract 2y on both sides, and you would divide by 3, and you would get -2/3 y. Ugh, fractions, not good. Well, what if we solve for y instead? Well, you would subtract 3x on both sides, and you would divide by 2, and then you would get -3/2 x. So maybe not the best option for substitution. However, we're going to do elimination. Specifically, we are going to eliminate y this time. You don't have to eliminate y. You can instead eliminate x, but I'm going to eliminate y. So our goal in elimination is to add or subtract these equations. But notice that if we add or subtract these equations right away, 3x plus 9x is 12x, 2y plus -4y is -2y equals 7. So we get 12x minus 2y equals 7, and then we still have an equation in one variable. That didn't do anything. So what we need to do is manipulate one of these two equations to get to a point where we can add or subtract and something will actually go away. So I flashed it on screen a little too quick, but why don't we multiply the top equation by 2? Maybe not obvious right away, but you'll see it in just a second. If we multiply the top equation by 2, 2 times 3x is 6x, 2 times 2y is 4y, 2 times 3 is 6. So make sure you multiply everything by 2. And now it's a little clearer why we chose to do it this way, because now if we add or subtract the equations, notice we have plus 4y and -4y. When we add them together, plus 4y minus 4y is just going to go away. 6x plus 9x is 15x. 6 plus 4 is 10. Divide both sides by 15. And 10 over 15 is 2/3. There we go. Really nice. This is elimination. Add or subtract the equations to eliminate one of the variables. And if you need to do the added step of manipulating one of the equations, that's totally fine too. All right. Well, we have x equals 2/3, but we need our y. So we're going to plug 2/3 back into either original equation. I'm going to plug it into the first. You can plug it into the second. Does not matter. All righty. Well, plugging in 2/3 for x. Well, 3 times 2/3, 3 cancels out. Subtract 2 on both sides, divide by 2. Then your answer is 2/3, 1/2. So solving systems of linear equations is quite nice. Either substitute or eliminate the variables. Okay. Like I said, you could have also plugged in 2/3 into any equivalent form, but I chose to just plug it into the first original equation. Okay, well, there's a 2/3 and 1/2, the solution to our system. Okay, let's solve this one via substitution again. Substitution, what we're going to do is solve the second equation for y. So we're going to add 2x to both sides. Well, from here, we have y equals 2x plus 9. So we're going to take this 2x plus 9 and plug it in for y in the first equation. Okay, and now once we're here, we substituted our y variable with the purpose of not having any more y's. Now we have just an equation and one variable. Let's distribute -5. Let's combine 2x and -10x. Let's add 45 to both sides, and let's divide both sides by -8. All of these steps in the top. So we have x equals -6, and now we're just going to plug in -6 into the second equation. 2 times -6 is -12. -12 plus 9 is -3. So the solution to our system is -6, -3. Okay, like I said, you could have plugged in x equals -6 to either original equation. I'm just happening to plug things into these. But if you plug -6 into either original, you would also get -3. There's your solution. All right, let's do it one more, or not one more. Let's do a couple more, but let's do this next one. 2x plus 3y equals 21. 3x minus 4y equals 23, and I want to solve this one via elimination. This time, I'm going to eliminate x. Last time, I think we eliminated y. This time, we're going to eliminate x. Well, notice 2x and 3x, there's nothing we can multiply 2x by to get rid of 3x, and there's nothing we can multiply 3x to get rid of 2x. So what we need to do is not just manipulate one of the equations, we need to manipulate both of them. So what number do we multiply 2x by, and what number do we multiply 3x by to get to a pair of factors, not a pair of factors, a pair of terms that can be canceled out? Well, what if we multiply 2x by 3 and 3x by 2? Well, maybe 3 times 2 is 6, 2 times 3 is 6. Maybe there's something fancy about 6 when it comes to 2 and 3. So multiply everything by 3 in the top, multiply everything by 2 in the bottom. And what we're now going to do, we have 6x and 6x. If we add 6x and 6x, we will get 12x. So instead, this time, let's subtract equations. What you could also do, you could multiply one of these by -3 or -2. Well, if you multiply it by negative, then the negative sign is already there, ready for you. But again, I'm just trying to show all the different ways you can solve these. So let's subtract these equations. 6x minus 6x is 0. It goes away. We eliminated x. 9y minus -8y. 9y minus -8y would be plus 8y. So 17y. 63 minus 46 is 17. Divide both sides by 17, and we get y equals 1. And now I think you guys get the idea. We can plug y equals 1 into either original equation or any equivalent form. So let's plug it into the second original equation, because why not? Well, plug in y equals 1, and now we're just going to solve for x. 4 times 1 is 4. Let's add 4 to both sides. Let's divide both sides by 3. Our answer is then 9, 1, x, y. Okay, there's our answer. Let's do another one. Let's solve this one via substitution. We're going to solve the first equation for y. Well, if we solve the first equation for y, then we're just going to subtract x on both sides. And now we're going to take 3 minus x and plug it in for y. So 3 minus x into second equation for y. And now we just have a linear equation for the second one. So let's solve that second equation for x. Let's distribute 2. Let's combine 2x minus 2x. 2x minus 2x goes away. So we're left with the equation that 6 equals 9. But 6 doesn't equal 9. So what did we do wrong? Well, actually nothing. So what we got is an inconsistent system. We got to a statement that was never true. So if we get one statement that is never true, that means the entire system is impossible to solve. So there is no solution to this system. However, another way you can look at it is like this. If we multiplied that second equation by 1/2, or divide everything by 2, however that works, right? Divide everything by 2 in the second equation. 1/2 times 2x is just x, 1/2 times 2y is just y, and look at that. We get 2 of the exact same equations, except we're saying the same two variables being added together need to add to 3, and the same two variables also need to add to 9/2. There's no way that the same two numbers can add to 3 and also add to 9/2. If we're going from a graphical standpoint, well, let's subtract x on both sides and look at this. These are two lines with the same slope but different y-intercepts. That's the definition of a parallel line. So there is no solution for that reason. So there are those two lines. Notice that they'll never meet. There can't be a solution. Okay, well, maybe you already have an idea on what's going to happen this time. So this time, why don't we multiply the second equation by 2 so that we can eliminate x. So if we have 4x and negative 2x, if we multiply this by 2, we get negative 4x, and 4x minus 4x is going to go away. Nice. All right. 2 times negative 2x, negative 4x. 2 times negative y, negative 2y. 2 times negative 6, negative 12. And now let's add these equations. So 4 plus negative 4x, or just 4 minus 4x, is 0. 2 plus negative 2y, 2y minus 2y is 0. And 12 plus negative 12 is also 0. Oh, did we do something wrong this time? Well, of course not. What we got this time is we found a statement that is always true in our system. Well, if we get to a point where the statement is always true, this is a dependent system and has all real solutions. Again, looking at it in a different way, well, what if we manipulate both of these equations to maybe look like each other? Well, let's multiply the first equation by 1/2, and let's multiply the second equation by negative 1. Well, 1/2 times 4x is 2x, 1/2 times 2y is y, 1/2 times 12 is 6, negative 1, change all of these signs, and notice that we have two of the exact same equation. Well, they're the same equation, they're the same line, so that system is dependent. So literally, I graphed both lines here, but you only see one of them because they overlap everywhere. Okay, so just some closing thoughts. We have two equations that give us a two-part coordinate, but what would three equations give us if we had three variables? A faster way, there's always a way that's faster, and this thing here, the system of linear equations, is actually the entire study of a class called linear algebra. This is a very, very small, very easy example that's like, it's like day one linear algebra, and you expand very quickly to solve systems of equations that might have 5 equations and 5 variables. And it's actually very neat. Linear algebra is a very fun class. So with that said, I'm not going to go over all the opposite methods. These methods were enough. But with that said, thank you so much for watching. And next time I see you, we will be back in chapter 3 for the final chapter of this algebra course. So with that said, bye.
Hi everyone, thank you so much for watching. I hope this lecture helped and that you learned something. Just wanted to give the brief disclaimer that this lecture for this section is based on and adapted from the section in College Algebra and Trigonometry, the 4th edition by J.S. Ratty, Marcus McWaters, and Leslavska Zerpek. So just wanted to give that disclaimer. I'm not affiliated with any of the authors. I'm not affiliated with Pearson, the publisher. This is entirely a presentation and lecture I created based on the book. So thank you so much for watching, and see you in the next section.